ყველაფერი აქვს მთებს კითხვებზე პასუხებისთვის მივადექი ღმერთს და მეც ვეღარ ნახავ მეც სხვაფერი აქვს დედამიწა სხვაფერი მაქვს მე მარტობით გაყინული ჩავეხუტე მზეს და მეც ვეღარ ნახავ მზეს დედამიწა ცადავლია მე მეგობრება დავრჩით ისევ მე და სიბნელე და მეც ვერ ვიმღერებ მეც სიბნელეში აირეკლა დაკარგული დღე დავემსგავსე სიგარეტის უკანასკნელ ღერს და მეც არ ვეგუები ყველაფერს ქვეყანას და რაფერი მაქვს მე ხდები უკვე როგორ დავემსგავსეთ ერთმანეთს და მე დავამთავრეთ ეს
სამი
სალამი ხალხებო წესით ხმა უნდა ისმოდეს გადავამოწმევთ და დავიწყოთ დღევანდელი დღე ეს არის
სამი
როგორ ჩანს ხმა ჩემი ხმა წესით ჩემი ხმაც არის აშასე აგვაქვს დღე რამდენადაც ხვდები ეს 20 ეს არის 25 ოკეი მოკლედ დღეს არის 25 ნოემბერი და თქვენ ესწრებით შესავალი კომპიუტერულ მეცნიერებებში კურსის მე-11 შეხვედრას დღევანდელ შეხვედრაზე განხილული იქნება მეოთხე კვირის მასალა მახსოვრობა და ლაბორატორიული სამუშაოები როგორც ვიცით, ჩანაწერები კეთდება და მოგვიანებით შეგიძლიათ ნახოთ ეს ყველაფერი. მითში შეგიძლიათ შემოხვიდეთ, მე დათო არმალანია. ეს დათოს ბლოგის მისამართია და დღეს დრო ზუსტად არ ვიცი, იმიტომ რომ პატარ-პატარა ვიდეოებია, როგორც იცით, ლაბებში. რაც შეეხება დღევანდელი ხუმრობა, დაახლოებით კი არა, ზუსტად ეს არის GTA-ს თამაშის დროს რო ისწავლა ტიპმა მანქანის ტარება. კარგით, შემდეგი რა გვაქვს? თქვენთვის მნიშვნელოვანია, რომ კოდი დაწეროთ თქვენ თვითონ. შემოგვიერთდით Facebook ჯგუფში. ეს არის თვითონის Teams-ის ჯგუფი, Discord-ის ჯგუფზე რატომღაც სიჩუმე არის ხოლმე. აგრეთვე YouTube-ში დაგვიკავშირდით და მოიწონეთ YouTube არხი და TikTok-ზე კიდევ თქვენ თვითონ შეგიძლიათ უფრო სწორედ აგვეხმაროთ TikTok-ის ამუშავებაში. და როგორც ვიცით და გითხარით, დღევანდელი შეხვედრა არის ლაბორატორიულები მახსოვრობის შესახებ. წინა შეხვედრებზე ვინც იყავით, იმედია მოგეწონათ ეს ლექციები და მე დარწმუნებით ვამბობ, რომ მსგავსი ტიპის ინფორმაციას თქვენ საქართველოში ნაკლებად თუ მიიღებთ. აქედან გამომდინარე, იმედია ლაბორატორიულებიც მოგეწონებათ და ეხლა ვეცდებით ჩავრთო სად არის ეს ყველაფერი მოთავსებული. ესე იგი, საიტი თვითონ მახსოვრობა ეს წინ გუშინდელი შეხვედრა არის. გუშინდელი შეხვედრის ლაივი არ დაიდება, იმიტომ რომ მნიშვნელოვანი ლექცია იყო და მე არაფერი მისაუბრია და ეს არის ქვია დღევანდელი შეხვედრის ვიდეოები. აქ მე-4-ს ჩავასწორებ, და გავხსოვთ. მიკროფონს გამორთავ და ლაბზე დავწყოთ პირველი შეხვედრა.
So, hexadecimal numbers, as if we need another base number scheme, right? Well, most Western cultures, as you probably are familiar, use the decimal system, base 10, to represent numeric data. We have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we need to represent values higher than 9, we can combine those digits using the notion of place value. So for 10, we have a 1 digit followed by a 0 digit, and we intuitively understand that what we're doing there is we're multiplying the first one by 10 and then adding 0 for a total of 10. Computers do something pretty similar, as you're probably familiar with the binary system, base 2, the difference there being that there are only 2 digits to work with, 0 and 1, and so our place values, instead of being 1, 10, 100, 1,000, as they would be in the decimal system, are 1, 2, 4, 8, and so on. Here's the thing though, those zeros and ones, especially if we're being computer scientists and we're doing a lot of programming, or we're working with computers, we're going to be seeing a lot of binary numbers. And those zeros and ones in large chains can be very difficult to parse, right? We can't just look at a string of zeros and ones and necessarily know exactly what it is. But it's still useful to be able to express data in the same way that a computer does. And so we have this notion of the hexadecimal system, which is base 16 instead of base 10 or base 2, which means that we have 16 digits to work with instead of 10 or 2. And it's a much more concise way to express binary information on a computer system. It's much more human understandable. So we have the digits 0 through 9, and then we also have these extra 6 digits, A, B, C, D, E, and F, which represent 10, our notion of 10, 11, 12, 13, 14, and 15 in decimal. Sometimes, by the way, you'll also see these A through Fs as capital A through F, which is the way I tend to do it. It's just my preferred style, but either is fine. They both represent pretty much the same thing. So why is hexadecimal cool? Why do we need to use this other additional base? We already have 2 and 10. Why do we need 16? Well, 16 is a power of 2. And so each hexadecimal digit, 0 through F, corresponds to a unique ordering or unique arrangement of 4 binary digits, 4 bits. And so in that sense, we can express very long, complex binary numbers in hexadecimal in a much more concise way without losing information or having to do particularly cumbersome conversions on those numbers. So as I just said, each hexadecimal digit corresponds to a unique arrangement of 4 binary digits. So the binary string 0000 corresponds to hexadecimal digit 0. 0110 corresponds to hexadecimal digit 6. And 1111 corresponds to hexadecimal digit F. If you're looking at this chart, particularly if you're looking at the left side of the chart, you can already see there's a bit of an ambiguity problem here, right? Decimal 0 is pretty much indistinguishable from hexadecimal 0, other than the fact that it's under a column that says hexadecimal, but we probably won't always have that column there. And so generally when we were expressing numbers in hexadecimal notation to clearly distinguish them from decimal notation, we usually prefix them with the prefix 0x. 0x means nothing in reality. It's just a clue to us as humans that what we're about to see or what we're about to have to start parsing is a hexadecimal number. Obviously for the higher digits A, B, C, D, E, and F, which correspond to 10 through 15, it's pretty unambiguous that that's a hexadecimal number. And in fact, any hexadecimal number that has letters in it is probably pretty obvious as a hexadecimal number. But still, for the sake of clarity, it's always a good idea to prefix every time you refer to a digit as a hexadecimal number by prefixing it with 0x. So binary, as we said, has place values. There's a 1's place, a 2's place, a 4's place, and an 8's place. And decimal also has place values, the 1's, 10's, 100's, and 1000s that you all may recall from grade school. And hexadecimal is no exception here, really. It also has place values, but instead of being powers of 2 or powers of 10, they're powers of 16. So when we see a number like this, we pretty clearly know it's 397, right? Well, if we see a number like this, we know this isn't 397 anymore. This is the hexadecimal number 397. It's not 397. It means something different because we're using powers of 16 as all of our place values instead of powers of 10. In fact, the place values here would be the 1's place, the 16's place, and the 256's place, which correspond to our idea of a 1's place, a 10's place, and a 100's place if the number was 397. But since it's 0x397, we have a 1's place, a 16's place, and a 256's place. Or a 16 to the 0 place, which is 1, a 16 to the first power place, 16, a 16 squared place, 256, and so on and so on and so on. So this number is really 3 times 16 squared plus 9 times 16 plus 7. I didn't do the math here, but it's not 397. It's much, much larger than that. Similarly, we could have 0x_ADC. Well, that's A times 16 squared, or if we translate that to our notion of decimal numbers, that's 10 times 16 squared, plus D times 16, or plus 13 times 16. And don't worry if you haven't memorized that D is 13 or anything like that. There's not too many of these letter digits, and it'll become intuitive pretty quickly. So again, this is 10 times 16 squared plus 13 times 16 plus 12 times 1, so 0x_ADC. So as I said, every group of 4 binary digits corresponds to a single hexadecimal digit, and so it's actually really easy to change back and forth between hex and binary. If you have this long string of binary digits, all you need to do is start grouping them right to left as groups of 4, and then you can consolidate them into hexadecimal numbers, severely limiting the number of digits you have to process mentally. Instead of 32 zeros and ones, as we'll see in a second, you might be able to get it down to just 8 hexadecimal digits. It's a lot more concise. The charts a few slides back will help you to kind of figure out this mapping, though you'll, again, memorize it pretty quickly. And we'll go through an example right now. So if we have a number like this really large binary number, or what appears to be a large binary number, and the only reason I say that is because it's just so, it's a behemoth, right? There's just so many zeros and ones there. But we probably don't really have a sense of what the magnitude of this number really is. We don't have any idea what it would correspond to in decimal, and in fact, we won't even see what it corresponds to in decimal right now, but we might be able to express this in a way that would give us some more information about just how big this number is. So let's go through that conversion process. The first thing we need to do is we want to group these digits out into groups of 4, starting from the right and working to the left. Now, there happen to be 32 digits here, which means we have a nice clean break of 8 groups of 4. So we have now, and remember that each group of 4 here uniquely corresponds to a hexadecimal digit. So we'll start, again, building our number from the right and working left. Well, what's 1101? Well, if we do the math out in our head, we have 1 in the 8th place, a 1 in the 4's place, a 0 in the 2's place, and a 1 in the 1's place. That's 8 plus 4 plus 1, which we would know as 13, but we probably wouldn't write 13 out because we're working with hexadecimal. We need to convert it to the hexadecimal equivalent of 13, which is D. 0011, well, that's a 0 in the 8th place, a 0 in the 4's place, a 1 in the 2's place, and a 1 in the 1's place, so that's 3. And we can keep doing this again. We have here 9, and then 11, but that's B, recall, 2, 10, or A, 6, and 4. And so that very large string of zeros and ones at the top is more concisely expressed in hexadecimal as 0x46A2 B9 3D. Well, okay, we've learned a new cool skill. What's the point? Well, you might not use this all the time. As we're going to soon see, we use hexadecimal quite a lot as programmers, not necessarily for the purpose of doing math with it, but because a lot of times memory addresses in our system are represented in hexadecimal. And so it's a really concise way to express otherwise cumbersome binary numbers. And so again, you're probably not going to do any math with it. You're not going to be multiplying hexadecimal numbers together or doing anything weird like that. But it is a useful skill to have so that you can express and understand memory addresses and other ways of using data in C. I'm Doug Lloyd. This is CS50. Pointers. Here we are. This is probably going to be the most difficult topic that we talk about in CS50. And if you've read anything about pointers before, you might be a little bit intimidated going into this video. It's true that pointers do allow you the ability to perhaps screw up pretty badly when you're working with variables and data and causing your program to crash. But they're actually really useful, and they allow us a really great way to pass data back and forth between functions that we're otherwise unable to do. And so what we really want to do here is train you to have good pointer discipline so that you can use pointers effectively to make your programs that much better. As I said, pointers give us a different way to pass data between functions. Now, if you recall from an earlier video when we were talking about variable scope, I mentioned that all the data that we pass between functions in C is passed by value. And I may not have used that term. What I meant there was that we are passing copies of data. When we pass a variable to a function, we're not actually passing the variable to the function, right? We're passing a copy of that data to the function. The function does what it will, and it calculates some value, and maybe we use that value when it gives it back. There was one exception to this rule of passing by value, and we'll come back to what that is a little later on in this video. If we use pointers instead of using variables, or instead of using the variables themselves, or copies of the variables, we can now pass the variables around between functions in a different way. This means that if we make a change in one function, that change will actually take effect in a different function. Again, this is something we couldn't do previously, and if you've ever tried to swap the value of two variables in a function, you've noticed this problem sort of creeping up, right? If we want to swap x and y, and we pass them to a function called swap, inside of the function swap, the variables do exchange values. 1 becomes 2, 2 becomes 1, but we don't actually change anything in the original function, in the caller, because we can't. We're only working with copies of them. With pointers, though, we can actually pass x and y to a function. That function can do something with them, and those variables' values can actually change. So that's quite a change in our ability to work with data. Before we dive into pointers, I think it's worth taking a few minutes to go back to basics here and have a look at how computer memory works, because these two subjects are actually going to be pretty interrelated. As you probably know, on your computer's system, you have a hard drive or perhaps a solid-state drive, some sort of file storage location. It's usually somewhere in the neighborhood of 250 gigabytes to maybe a couple of terabytes now. And it's where all of your files ultimately live. Even when your computer is shut off, you can turn it back on, and you'll find your files are there again when you reboot your system. But disk drives, like a hard disk drive, an HDD, or a solid-state drive, an SSD, are just storage space. We can't actually do anything with the data that is in hard disk or in a solid-state drive. In order to actually change data or move it around, we have to move it to RAM, random access memory. Now, RAM you have a lot less of in your computer. You may have somewhere in the neighborhood of 512 megabytes if you have an older computer, to maybe 2, 4, 8, 16, possibly even a little more gigabytes of RAM. So it's much smaller, but that's where all of the volatile data exists. That's where we can change things. But when we turn our computer off, all of the data in RAM is destroyed. So that's why we need to have hard disk for the more permanent location of it, so that it exists. It would be really bad if every time we turned our computer off, every file in our system was obliterated. So we work inside of RAM, and every time we're talking about memory, pretty much in CS50, we're talking about RAM, not hard disk. So when we move things into memory, it takes up a certain amount of space. All of the data types that we've been working with take up different amounts of space in RAM. So every time you create an integer variable, 4 bytes of memory are set aside in RAM so that you can work with that integer. You can declare the integer, change it, assign it to a value 10, increment it by 1, so on and so on. All of that needs to happen in RAM, and you get 4 bytes to work with for every integer that you create. Every character you create gets 1 byte. That's just how much space is needed to store a character. Every float, a real number, gets 4 bytes, unless it's a double precision floating point number, which allows you to have more precise or more digits after the decimal point without losing precision, which take up 8 bytes of memory. Long longs, really big integers, also take up 8 bytes of memory. How many bytes of memory do strings take up? Well, let's put a pin in that question for now, but we'll come back to it. So back to this idea of memory as a big array of bite-sized cells. That's really all it is. It's just a huge array of cells, just like any other array that you're familiar with in C, except every element is 1 byte wide. And just like an array, every element has an address. Every element of an array has an index, and we can use that index to do so-called random access on the array. We don't have to start at the beginning of the array, iterate through every single element thereof to find what we're looking for. We can just say, I want to get to the 15th element or the 100th element. And you can just pass in that number and get the value you're looking for. Similarly, every location in memory has an address. So your memory might look something like this. Here's a very small chunk of memory. This is 20 bytes of memory, the first 20 bytes, because my addresses there at the bottom are 0, 1, 2, 3, and so on, all the way up to 19. And when I declare variables, when I start to work with them, the system is going to set aside some space for me in this memory to work with my variables. So I might say char C equals capital H. And what's going to happen? Well, the system is going to set aside for me 1 byte. In this case, it chose byte number 4, the byte at address 4. And it's going to store the letter capital H in there for me. If I then say int speed limit equals 65, it's going to set aside 4 bytes of memory for me. And it's going to treat those 4 bytes as a single unit because what we're working with is an integer here. And it's going to store 65 in there. Now, already I'm kind of telling you a bit of a lie, right? Because we know that computers work in binary. They don't understand necessarily what a capital H is or what a 65 is. They only understand binary, zeros and ones. And so actually what we're storing in there is not the letter H and the number 65, but rather the binary representations thereof, which look a little something like this. And in particular, in the context of the integer variable, it's not going to just spit it into, it's not going to treat it as one 4-byte chunk necessarily. It's actually going to treat it as 4 1-byte chunks, which might look something like this. And even this isn't entirely true either because of something called endianness, which we're not going to get into now, but if you're curious about, you can read up on little and big endianness. But for the sake of this argument, for the sake of this video, let's just assume that that is in fact how the number 65 would be represented in memory on every system, although that's not entirely true. But let's actually just get rid of all the binary entirely and just think about it as H and 65. It's a lot easier to think about it like that as a human being. All right, so it also seems maybe a little random that my system didn't give me bytes 5, 6, 7, and 8 to store the integer. There's a reason for that too, which we won't get into right now. But suffice it to say that what the computer is doing here is probably a good move on its part to not give me memory that's necessarily back to back, although it's going to do it now if I want to get another string called surname and I want to put Lloyd in there. I'm going to need to fit one character. Each letter of that's going to require one character, 1 byte of memory. So if I can put Lloyd into my array like this, I'm pretty good to go, right? What's missing? Remember that every string we work with in C ends with \0, and we can't omit that here either. We need to set aside 1 byte of memory to hold that so we know when our string has ended. And so again, this arrangement of the way things appear in memory might be a little random, but it actually is how most systems are designed, to line them up on multiples of 4, for reasons, again, that we don't need to get into right now. But this, so suffice to say, after these 3 lines of code, this is what memory might look like. If it assigned me memory locations 4, 8, and 12 to hold my data, this is what my memory might look like. And just to be particularly pedantic here, when we're talking about memory addresses, we usually do so using hexadecimal notation. So why don't we convert all of these from decimal to hexadecimal notation, just because that's generally how we refer to memory. So instead of being 0 through 19, what we have is 0x0 through 0x13. Those are the 20 bytes of memory that we're looking at in this image right here. So all of that being said, let's step away from memory for a second and back to pointers. Here is the most important thing to remember as we start working with pointers. A pointer is nothing more than an address. I'll say it again because it's that important. A pointer is nothing more than an address. Pointers are addresses to locations in memory where variables live. Knowing that, it becomes hopefully a little bit easier to work with them. Another thing I like to do is to have sort of diagrams visually representing what's happening with various lines of code. And we'll do this a couple of times in pointers and when we talk about dynamic memory allocation as well, because I think that these diagrams can be particularly helpful. So if I say, for example, int k in my code, what is happening? Well, what's basically happening is I'm getting memory set aside for me. But I don't even like to think about it like that. I like to think about it like a box. I have a box, and it's colored green because I can put integers in green boxes. If it was a character, I might have a blue box. But I always say, if I'm creating a box that can hold integers, that box is colored green. And I take a permanent marker and I write k on the side of it. So I have a box called k into which I can put integers. So when I say int k, that's what happens in my head. If I say k equals 5, what am I doing? Well, I'm putting 5 in the box, right? This is pretty straightforward. If I say int k, create a box called k. If I say k equals 5, put 5 into the box. Hopefully that's not too much of a leap. Here's where things get a little interesting, though. If I say int star pk, well, even if I don't know what this necessarily means, it's clearly got something to do with an integer. So I'm going to color this box greenish. I know it's got something to do with an integer, but it's not an integer itself because it's an int star. There's something slightly different about it. So an integer is involved, but otherwise it's not too different from what we were talking about. It's a box. It's got a label. We're going to label this one pk, and it's capable of holding int stars, whatever those are. They have something to do with integers, clearly. Here's the last line, though. If I say pk equals ampersand k, whoa, what just happened, right? So this random number, seemingly random number, gets thrown into the box there. All that is pk gets the address of k. So I'm sticking where k lives in memory, its address, the address of its bytes. All I'm doing is I'm saying that value is what I'm going to put inside of my box called pk. And because these things are pointers, and because looking at a string like 0x80c74820 is probably not very meaningful, when we generally visualize pointers, we actually do so as pointers. pk gives us the information we need to find k in memory. So basically, pk has an arrow in it, and if we walk the length of that arrow, imagine it's something that you can walk on. If we walk along the length of the arrow, at the very tip of that arrow, we will find the location in memory where k lives. And that's really important because once we know where k lives, we can start to work with the data inside of that memory location, though we're getting a teeny bit ahead of ourselves for now. So what is a pointer? A pointer is a data item whose value is a memory address. That was that 0x80 stuff going on. That was a memory address. That was a location in memory. And the type of a pointer describes the kind of data you'll find at that memory address. So there's the int star part, right? If I follow that arrow, it's going to lead me to a location. And that location, what I will find there, in my example, is a green colored box. It's an integer. That's what I will find if I go to that address. So the data type of a pointer describes what you will find at that memory address. So here's the really cool thing, though. Pointers allow us to pass variables between functions and actually pass variables and not pass copies of them. Because if we know exactly where in memory to find a variable, we don't need to make a copy of it. We can just go to that location and work with that variable. So in that sense, pointers sort of make a computer environment a lot more like the real world, right? So here's an analogy. Let's say that I have a notebook, right? And it's full of notes, and I would like you to update it. You are a function that updates notes, right? In the way we've been working so far, what happens is you will take my notebook, you'll go to the copy store, you'll make a Xerox copy of every page of the notebook, you'll leave my notebook back on my desk when you're done, you'll go and cross out things in my notebook that are out of date or wrong, and then you'll pass back to me the stack of Xerox pages that is a replica of my notebook with the changes that you've made to it. And at that point, it's up to me as the calling function, as the caller, to decide to take your notes and integrate them back into my notebook. So there's a lot of steps involved here, right? Like, wouldn't it be better if I just say, hey, can you update my notebook for me, hand you my notebook, and you take things and literally cross them out and update my notes in my notebook, and then give me my notebook back? That's kind of what pointers allow us to do. They make this environment a lot more like how we operate in reality. All right, so that's what a pointer is. Let's talk about how pointers work in C and how we can start to work with them. So there's a very simple pointer in C called the null pointer. The null pointer points to nothing. This probably seems like it's actually not a very useful thing, but as we'll see a little later on, the fact that this null pointer exists actually really can come in handy. And whenever you create a pointer and you don't set its value immediately, an example of setting its value immediately would be a couple slides back where I said pk equals ampersand k. pk gets k's address, as we'll see what that means. We'll see how to code that shortly. If we don't set its value to something meaningful immediately, you should always set your pointer to point to null. You should set it to point to nothing. That's very different than just leaving the value as it is, than declaring a pointer and just assuming it's null, because that's rarely true. So you should always set the value of a pointer to null if you don't set its value to something meaningful immediately. You can check whether a pointer's value is null using the equality operator equals equals, just like you can compare any integer values or character values using equals equals as well. It's a special sort of constant value that you can use to test. So that was a very simple pointer, the null pointer. Another way to create a pointer is to extract the address of a variable you've already created. And you do this using the ampersand operator, address extraction, which we've already seen previously in the first diagram example I showed. So if x is a variable that we've already created of type integer, then ampersand x is a pointer to an integer. Ampersand x is, remember, ampersand is going to extract the address of the thing on the right. And since a pointer is just an address, then ampersand x is a pointer to an integer whose value is where in memory x lives. It's x's address. So ampersand x is the address of x. Let's take this one step further and connect to something I alluded to in a prior video. If ARR is an array of doubles, then ampersand ARR square bracket I is a pointer to a double. Okay? ARR square bracket I, if ARR is an array of doubles, then ARR square bracket I is the ith element of that array. And ampersand ARR square bracket I is where in memory the ith element of ARR exists. So what's the implication here? An array's name, the implication of this whole thing, is that an array's name is actually itself a pointer. You've been working with pointers all along every time that you've used an array. Remember from the example on variable scope. Near the end of the video, I present an example where we have a function called setInt and a function called setArray, and you're challenged to determine whether or not, or what the values will be printed out at the end of the function, at the end of the main program. If you recall from that example, or if you've watched the video, you know that when the call to setInt effectively does nothing, but the call to setArray does. And I sort of glossed over why that was the case at the time. I just said, well, it's an array, it's special, there's a reason. The reason is that an array's name is really just a pointer. And there's this special square bracket syntax that make things a lot nicer to work with, and they make the idea of a pointer a lot less intimidating, and that's why they're sort of presented in that way. But really, arrays are just pointers, and that's why when we made a change to the array, when we passed an array as a parameter to a function or as an argument to a function, the contents of the array actually changed in both the callee and in the caller, which for every other kind of variable we saw was not the case. So that's just something to keep in mind when you're working with or pointers, is that the name of an array is actually a pointer to the first element of that array. Okay, so now we have all these facts. Let's keep going, right? Why do we care about where something lives? Well, like I said, it's pretty useful to know where something lives so you can go there and change it, and work with it, and actually have the thing that you want to do to that variable take effect and not take effect on some copy of it. This is called dereferencing. We go to the reference and we change the value there. So if we have a pointer and it's called PC and it points to a character, then we can say star PC. And star PC is the name of what we'll find if we go to the address PC. What we'll find there is a character, and star PC is how we refer to the data at that location. So we could say something like star PC equals capital D, or something like that, and that means that whatever was at memory address PC, whatever character was previously there, is now capital D if we say star PC equals capital D. So here we go again with some weird C stuff, right? So we've seen star previously as being somehow part of the data type, and now it's being used in a slightly different context to access the data at a location. I know it's a little confusing, and that's actually part of this whole, why pointers have this mythology around them of being so complex. It's kind of a syntax problem, honestly. But star is used in both contexts, both as part of the type name, and we'll see a little later something else too, and right now as the dereference operator. So it goes to the reference. It accesses the data at the location of the pointer and allows you to manipulate it at will. Now this is very similar to visiting your neighbor, right? If you know where your neighbor lives, you're not hanging out with your neighbor. You happen to know where they live, but that doesn't mean that by virtue of that, having that knowledge, you are interacting with them. If you want to interact with them, you have to go to their house. You have to go to where they live. And once you do that, then you can interact with them just like you'd want to. And similarly with variables, you need to go to their address if you want to interact with them. You can't just know the address. And the way you go to the address is to use star, the dereference operator. What do you think happens if we try and dereference a pointer whose value is null? Recall that the null pointer points to nothing. So if you try and dereference nothing, or go to an address nothing, what do you think happens? Well, if you guessed segmentation fault, you'd be right. If you try and dereference a null pointer, you suffer a segmentation fault. But wait, didn't I tell you that if you're not going to set your value of your pointer to something meaningful, you should set it to null? I did, and actually the segmentation fault is kind of a good behavior. Have you ever declared a variable and not assigned its value immediately? So you just say int x semicolon. You don't actually assign it to anything, and then later on in your code you print out the value of x having still not assigned it to anything? Frequently you'll get 0, but sometimes you might get some random number and you have no idea where it came from. Similarly, can things happen with pointers? When you declare a pointer, int star pk, for example, and you don't assign it to a value, you get 4 bytes from memory, whatever 4 bytes of memory the system can find that have some meaningful value. And there might have been something already there that is no longer needed by another function, so you just have whatever data was there. What if you tried to dereference some address that you don't, there were already bytes and information in there that's now in your pointer. If you try and dereference that pointer, you might be messing with some memory that you didn't intend to mess with at all. And in fact, you could do something really devastating like break another program or break another function or do something malicious that you didn't intend to do at all. And so that's why it's actually a good idea to set your pointers to null if you don't set them to something meaningful. It's probably better at the end of the day for your program to crash than for it to do something that screws up another program or another function. That behavior is probably even less ideal than just crashing. And so that's why it's actually a good habit to get into, to set your pointers to null if you don't set them to a meaningful value immediately, a value that you know and that you can safely dereference. So let's come back now and take a look at the overall syntax of the situation. If I say int star p semicolon, what have I just done? What I've done is this. I know that the value of p is an address, because all pointers are just addresses. I can dereference p using the star operator. In this context here at the very top, recall, the star is part of the type. It's int star is the data type. But I can dereference p using the star operator. And if I do so, if I go to that address, what will I find at that address? I will find an integer. So int star p is basically saying p is an address. I can dereference p, and if I do, I will find an integer at that memory location. Okay, so I said that there was another annoying thing with stars, and here's where that annoying thing with stars is. Have you ever tried to declare multiple variables of the same type on the same line of code? So for a second, pretend that the code I actually have there in green isn't there, and it just says int x, comma y, comma z, semicolon. What that would do is actually create 3 integer variables for you, one called x, one called y, and one called z. It's a way to do it without having to split it onto 3 lines. Here's where stars get annoying again, though, because the star is actually part of both the type name and part of the variable name. And so if I say int star px, comma py, comma pz, what I actually get is a pointer to an integer called px and 2 integers, py and pz. And that's probably not what we want. That's not good. So if I want to create multiple pointers on the same line of the same type, int stars, what I actually need to do is say int star pa, comma star pb, comma star pc. Now, having just said that and now telling you this, you probably will never do this. And it's probably a good thing, honestly, because you might inadvertently omit a star or something like that. It's probably best to maybe declare pointers on individual lines. But it's just another one of those annoying syntax things with stars that make pointers so difficult to work with, because it's just this syntactic mess you have to work through. With practice, it does really become second nature. I still make mistakes with it, still after programming for 10 years. So don't be upset if it's something that happens to you. It's pretty common, honestly. It's really kind of a flaw of the syntax. Okay, so I kind of promised that we would revisit the concept of how large is a string. Well, if I told you that a string, we've really kind of been lying to you the whole time. There's no data type called string. And in fact, I mentioned this in one of our earliest videos on data types, that string was a data type that was created for you in CS50.h. You have to pound include CS50.h in order to use it. Well, string is really just an alias for something called a char star, a pointer to a character. Well, pointers, recall, are just addresses. So what is the size in bytes of a string? Well, it's 4 or 8. And the reason I say 4 or 8 is because it actually depends on the system. If you're using CS50 IDE, char stars, the size of a char star is 8. It's a 64-bit system. Every address in memory is 64 bits long. If you're using CS50 appliance or you're using any 32-bit machine, and you've heard that term 32-bit machine, what is a 32-bit machine? Well, it just means that every address in memory is 32 bits long. And so 32 bits is 4 bytes. So a char star is 4 or 8 bytes depending on your system. And indeed, any data types, and a pointer to any data type, since all pointers are just addresses, are 4 or 8 bytes. So let's revisit this diagram and let's conclude this video with a little exercise here. So here's the diagram we left off with at the very beginning of the video. So what happens now if I say star pk equals 35? So what does it mean when I say star pk equals 35? Take a second. Star pk. In context here, star is dereference operator. So when the dereference operator is used, we go to the address pointed to by pk, and we change what we find. So star pk equals 35 effectively does this to the picture. So it's basically syntactically identical to having said k equals 35. One more. If I say int m, I create a new variable called m, a new box. It's a green box because it's going to hold an integer, and it's labeled m. If I say m equals 4, I put an integer into that box. If I say pk equals ampersand m, how does this diagram change? Pk equals ampersand m. Do you recall what the ampersand operator does or is called? Remember that ampersand, some variable name, is the address of a variable name. So what we're saying is pk gets the address of m. And so effectively what happens in the diagram is that pk no longer points to k, but points to m. Again, pointers are very tricky to work with, and they take a lot of practice. But because of their ability to allow you to pass data between functions and actually have those changes take effect, getting your head around them is really important. It probably is the most complicated topic we discuss in CS50, but the value that you get from using pointers far outweighs the complications that come from learning them. So I wish you the best of luck learning about pointers. I'm Doug Lloyd. This is CS50. As we continue to put So if you've seen our video on structures, you already know that we have the ability to define our own data types. But if you've used structures, you know that sometimes using those data types can actually be a little cumbersome because we have to use the struct keyword when we're working with them. Struct car or struct student. That's a lot to type if we just want to have something simple like a structure. We want to be able to work with things a little more shorthand way like int or char, something a lot more convenient to type. Fortunately, there's a way to do this in C with something called typedef, which is a way to create shorthand or rewritten names for data types. You can rewrite data types that already exist, or you can write data types of your own. The first thing you do is you define a type in the normal way, and then you just alias it to something else. Typedef, old name, new name. Pretty straightforward, right? So we could typedef, for example, the already existing data type of unsigned char as byte. And then from now on, after we've made this type definition, again, which is usually going to be at the top of our .c files or in a .h file separately, we can just use byte everywhere we would have used unsigned char. That's a lot shorter to type. In CS50's library, we do this. We typedef char star as string because we abstracted away the idea of pointers and the fact that a string is really a pointer to the first character in an array of characters because it's just so confusing to get your head around that. But in fact, that's what we do. And this line of code actually exists in CS50.h, typedef char star string, just to make that a little less cumbersome to have to deal with. Already you've seen probably a little bit of the value here, but typedef becomes great when combined with structures, as I alluded to earlier. Structures have a two-word type name, and so they can be really annoying to create variables of that type or malloc size of struct something. Your lines can just get really, really long. And so you can use typedef to come up with something a lot shorter. So if I define a car as follows, I have my definition of a car, struct car, and then open curly brace, all the fields of my structure, close curly brace, semicolon. After I've defined my data type, I can typedef struct car as car underscore t. And then when I've done that, now every time I would have otherwise used struct car, I can just use car underscore t. That's a lot shorter of a way to express this idea of this structure that I just created. Alternatively, because structures are so commonly used in typedef, you can actually define the type in between the start and the end. So the typedef structure, again, is usually typedef, old name, new name, where the names are already types that you've created, but you can actually define a structure right in the middle of the typedef instead of having to define it separately and then do a typedef of it. And that would look just like this: typedef struct car, open curly brace, all of your field definitions, close curly brace, car t. So the old name is all of that stuff in red. You're just defining the structure and naming it at the same time. And then the new name is car underscore t. And so if we start to use this in code, previously I might have said struct car my car semicolon. Well, I don't have to do that anymore. Now that I've used the typedef, I can just say car underscore t my car. That's a lot shorter of a way to do it, and in fact, it's going to be a lot more convenient, especially as you start to use structures a lot more in your code. I'm Doug Lloyd. This is CS50. So in this video, we're going to talk about how to dynamically allocate memory in C. Now, as a disclaimer, if you haven't watched our video on pointers or aren't generally familiar with the concept of pointers, you're probably going to want to go take a look at that before this. This video, dynamic memory allocation in general, works specifically with pointers, so you're going to want to make sure that you're comfortable with that before diving into this particular video. Without further ado, let's get started. Now, we've already seen how to work with pointers before, but typically we've only done it in the context of pointing a pointer variable that we declare statically at another variable that already exists. You may recall from our video on pointers, we had a line like int x equals 5, and then we would say int star px equals ampersand x. But that's the only way we've seen how to work with pointers, and that's static pointer usage, basically. In order to work with pointers statically, as we have, we need to know exactly how much memory we're going to use at the moment we compile our program. So we're not going to be creating any memory on the fly. All the memory that we're going to use is already set up when we begin. That presents sort of an issue, right? What if we don't know how much memory we're going to have when we get started? Maybe you're going to be asking the user to give you a number, and they're going to generate 100 linked list objects. Or they're going to generate 100 of something, and you don't know that. Or maybe they generate 200 or 400. We wouldn't be able to predict this in advance. And so we need to use dynamic memory allocation in order to get new memory in our program while the program is already running. And that's a little bit different than anything we've seen before. We can do this by allocating memory from something called the heap. The heap is a giant pool of memory, and so far the only pool of memory that we're familiar with is called the stack. But dynamically allocated memory comes from the heap, and statically allocated memory, which is anything that you give a name to, typically like a variable name, is going to be set up on the stack, and anything that you create dynamically while your program is running is going to come from the heap. But as we can see from this diagram, the stack and the heap are actually the same big chunk of memory. It just so happens that the stack we allocate from the bottom to the top. Typically we visualize it. So the stack memory addresses will be a bit lower numbers, and the heap will have higher numbers, and they'll allocate downward. So it's really one giant pool of memory, but we call it two different things depending on how it's being used. The stack for statically declared memory grows up, and the heap for dynamically allocated memory grows down. How do we get at this dynamically allocated memory? How do we access memory on the heap? We need to use a new function called malloc. You can get malloc by including standardlib.h, stdlib.h, and the only argument that you need to pass to malloc is how many bytes of memory that you want. So if you want an integer, you say malloc 4. If you want a character, you malloc 1. If you want a double, you malloc 8, and so on. And you can be more complex than that, as we'll soon see. What malloc will then try and do is find some chunk of memory the size that you asked for on the heap. So it'll go and try and find 8 contiguous bytes of memory. For example, if we're allocating a double, it will go and try and find 8 contiguous bytes of memory from the heap. And what it will do is it will return to you a pointer to that memory, right? So the only way we're going to be able to access dynamically allocated memory or use it is by dereferencing the pointer that we get back from malloc. And that's why it's important to understand pointers before going forward. Now, it's possible that malloc might not actually be able to give you back memory, in which case it's going to return to you null. And so one of the first rules to remember about dynamically allocating memory is to always check for null after malloc. Now, why might this happen? Maybe you've run out of memory, the stack and the heap have just completely run out, or there's been some sort of catastrophic failure that we can't predict. But either way, if you recall from our pointers video, dereferencing a null pointer, bad news. So the first thing you want to do after you malloc, of course, is to check to make sure that you didn't get back null. And if you did, you're going to need to abort your program because something has gone wrong and you can't proceed with what you currently have. So if we want to just get an integer, statically declare it, we can just say int x. That's going to create a variable called x on the stack that we can then assign any value that we like to. If you want to dynamically allocate an integer, we say the following: int star px equals malloc 4. And the reason we say 4 here is because there are 4 bytes in an integer. I easily also could have used the size of operator, which is available in C. Basically, you pass it a type. So it's a little bit different. Usually with functions, you pass in a variable. With malloc, you pass in, or with size of rather, you pass in a type, and it will return how many bytes that type takes up on the system. So int star px equals malloc size of int, or int star px equals malloc 4, basically means malloc is going to go try and find you 4 bytes of memory that are next to each other on the heap, and malloc will return to you a pointer to that memory called px. And then we could dereference that pointer, as we've seen in the pointers video, to manipulate it, to put a value in there, to do whatever we want to do with it. Let's see another example of this. Maybe we want to get an integer from the user. So recall that in CS50 we have the getInt function that we can use. Int x equals getInt. We're basically prompting the user for some integer value, and they'll give us some number, hopefully in this example a positive number. Let's say I want to declare an array of that many floats on the stack. I can do this by saying float stack array, and then in square brackets, which again indicates the size of the array, x. This is legal in C99 and C11. If you're using a very old version of C, this was actually previously not allowed, but you can do this. We can basically get a variable-sized array on the stack, which we're doing here because we don't know how big it's going to be in advance. We're just getting it from the user. But this is how we would declare an array of floats on the stack, where the number of items in that array is the number the user just gave us. And I can also dynamically allocate an array of floats on the heap, not on the stack, remember, because we're dynamically allocating the memory this time. Float star heap array, so that's my pointer to the memory that I'm getting. And I want to malloc x times the size of a float. So if I want to have 50 floats, I need 50 times the size of a float. So 50 times 4. Maybe I want 100, so it'd be 100 times 4. So that's why we're doing the multiplication there. And malloc is going to return to us one giant block of memory, that size, which we can then just treat like any other array. There's one catch with dynamically allocated memory, though, that we have to deal with, and that's something that we haven't seen before, and that is that it is not released back to the system when you are done. So if you haven't yet seen our video on the call stack or stack frames, this might not be something you're aware of yet, but typically when a function finishes running, what happens is all of the memory that was created for purposes of that function's existence gets destroyed, and it is released back to the system to be used somewhere else. So another function call that might come up can use that same bit of memory before. That's kind of convenient, right? This system is constantly recycling where it can. But when you tell the system, I want a block of memory, the system is not going to assume anything about it. It's not going to assume that, it hasn't seen you make a call with it for 50 lines or whatever, and it's just going to dynamically free it or release it back to the system. And if you fail to release enough memory back to the system, what you get is something called a memory leak. And memory leaks are really not good because they can really slow down your system. And in fact, there are some browsers that shall remain nameless that are sort of notorious for not freeing memory or not releasing memory back to the system when it's done. And that can really cause your computer to slow down because that browser is basically hogging a bunch of memory, and the other programs on your computer can't use it because the browser has sort of allocated it and said, no, this is mine, I need it, but it never releases it back to be shared by the other things on the system. So that's why if you leave a browser open for like days, or some browsers open for days or weeks, you might notice your computer starts to slow down. Now the rule is, as I mentioned before, when you're done working with dynamically allocated memory, all you have to do is free it. And free is another function that is available in standard lib.h. And basically what you pass to free is a pointer to any memory that you have dynamically allocated previously. And basically that's just telling the system, I'm done, you can use this memory for whatever you'd like. So here's another example. Let's say we want to malloc a 50 character long array. So basically a big string, we're going to call it word. We dynamically allocate it. Then we just do some stuff with it. Maybe we're in the middle of a function. We're changing its value, we're assigning new characters, we're printing it out, for example, and then we decide that we're done with it. How do we release this back to the system? We just need to free it. So we free word. Word is the pointer to that block of memory. That's the thing that we want to free. So there are three basic rules for malloc and free that are really important to internalize. The first is that everything that you malloc has to be freed before your program finishes running. Now granted, if your program actually finishes running, once it's completely done, once you've returned 0 from main, for example, then it will be freed. But it's a good practice to make sure that everything that you allocate, you specifically free by explicitly calling the free function, as opposed to just relying on the system to do it once your program is completely done. So everything that you malloc, you have to free. Rule number 2, only things that you malloc are things that you should free. So if you statically declared a variable, you don't want to free it. The system is going to take care of releasing all statically declared memory for you. It's only dynamically allocated memory, only memory that you malloc are things that you should free. And then make sure not to free the same block of memory more than once, because that can create a problem of a double free, and you have sort of an inverse memory leak, like a memory flow or something, where you trick the system into thinking that you have more memory than you do. It's not the kind of thing that you actually want to do. So remember, everything you malloc, you should free. Only things that you malloc, you should free. And don't free anything more than once. Let's just close this video by taking a look at a couple of lines of code and a visual example to show you exactly what's happening as we do it. So first, let's statically declare an integer called m. And so this would look something like this. I've colored the box green because in my head, sort of integers are always in green boxes, and I've written the label m on the box. Then I'm going to say int star a. So here I'm statically declaring a pointer called a. So recall that I like to think of it's an int star, so it's int like, so it'll be green. It's a greenish box. It's not a green box because that's for ints, but int stars are sort of greenish. They refer to ints. So this is another box, and this one is called a. Then I can say int star b equals malloc size of int. So what's going to happen here? Well, I'm going to have something called b that I'm giving a name to, so that's going to be sort of a light greenish box. And I'm asking malloc to dynamically give me 1 int's worth of space. And so what actually happens sort of visually is this. Notice that the actual integer, I didn't give a name to. I don't have a name for it. It's one way, typically, that I know I don't have a statically declared integer. The only way that I can refer to that green box is by dereferencing the pointer called b. So b has a name, that's statically declared, but I dereference b in order to get to this dynamically allocated memory. And of course, I'm not going to do this here, but the first thing I should do immediately after this is check to make sure that b is not null. If b is null, something has gone wrong. I need to stop my program immediately. Next, I can say something like this, a equals ampersand m. If you recall from our video on pointers, basically this just means a points to m, so that just creates this arrow here. Next up, let's say a equals b. Before I show you what's going to happen here, can you try and guess a little bit about what it's going to be? Take a look at the diagram. Think about how relationships might change. If I say a equals b, what am I saying? What I'm saying is that a and b are now going to point to the same location. In particular, a is going to point where b currently points. And so instead of pointing to m, a is now going to point over here to this dynamically allocated block that I can currently only reference. Now I can reference it multiple ways. Now I could say star A or star B. I can reference it either way because both of those same statically declared variables point to the same location. I can then say m equals 10. That's not a problem because 10 was statically declared. It's a box that I know about already. It's got a name. So when I say m equals 10, I'm just saying put 10 into this green box called m. Star B equals m plus 2. It's a little weird, right? But what's m plus 2? Well, m is 10, so 10 plus 2 is 12. And star b equals 12. When I say star b, I'm dereferencing b, so I'm going to travel along the arrow to where b points, and I'm going to put 12 in that location. Okay? Next up, I'm going to free b. So remember what happens with free is we are telling the system we're no longer working with this, we're done. You can take these 4 bytes back, or whatever the size of this is. This one happens to be 4 bytes. You can take it back and use it for whatever you want in some other program. So when I free b, this memory basically goes away. A and b still point to where it used to be, but I no longer have access to it. If I try and touch it, the system might get upset with me. So for example, if I try and say this, star a equals 11, what's going to happen? Unpredictable behavior, right? We don't know. We might get a segmentation fault because we're touching memory that we're no longer we don't have write privileges to anymore. You might get away with it, depends on where that memory happened to live on the system, but it's unpredictable. So once you free memory, remember, you're telling the system, I don't need it anymore. So if you then try and use it, some strange things might result. Dynamic memory allocation is a little strange to get used to because we're so used to this idea of creating a variable and assigning it a value and just manipulating it in that way that using pointers to sort of control where memory is and change it indirectly through pointers can be a bit strange, but just keep practicing with it. Internalize those rules about how to malloc and free successfully to make sure that you don't create memory leaks or anything like that, and you should be off to a good start. I'm Doug Lloyd. This is CS50. If you saw our video on recursion, the process might have seemed a little bit magical, right? Like, how does a function know to wait for another function and pass its data to some other thing that's running at the same time? It can seem a little magical at the outset if you don't understand exactly how functions are called and operate in C. And the way they operate is using something called the call stack. And the way the call stack works is as follows. If you call a function, basically what happens is a big chunk of memory is set aside somewhere on the system for that function to do its work. So for example, if you call a function and the first thing you do is declare a couple of variables, what's going to happen is a stack frame or a function frame will be created, a big chunk of memory, and those variables will be given space. So if it's 3 integers, you'll get 3 4-byte chunks, just like the size of an integer, as well as some space to do some calculations and whatever else the function might need. And that's where the function will do all of its work. Now, it's possible that more than one function's frame might exist in memory at any given time. So for example, let's say the function main calls another function called move. And then the function move calls another function called direction. At that point, all 3 of those functions have open frames. But in general, only one of those frames will ever be active. Only one of those functions is ever running at a given time, even though all 3 of them have space set aside and are sort of like hanging out, waiting to do something. Now, the way these frames are arranged is in what's called a stack. And the frame for the most recently called function is always the one at the top of the stack, and that is called the active frame. So again, if main called move and move called direction, you can think about this like a stack as follows, where main is at the bottom, move is above it, direction is on the top, and direction is the active frame. That is the only function that is doing anything at the moment, whereas move and main are just sort of like waiting to become the active frame. They're waiting to become the frame that is at the top of the stack. When you call a new function, a new frame is what's called pushed onto the top of the stack. So if you call a new function, that function immediately gets space in memory and is put on top of the call stack, and it becomes the active frame. And whatever was the active frame, if there was one, is kind of on pause. It's just sitting there kind of like it's in a holding pattern, waiting to become the active frame again. When a function finishes its work, such as by returning most commonly, or perhaps reaching the end of the line if it's a void function and doesn't have a return value, that frame is what's called popped off of the stack. And then the frame that was in second place, since this frame is now gone, that becomes the active frame. It resumes where it left off. If you would hit pause on that function, it's going to pick up immediately where it left off. This is actually why recursion works, because all of these frames are running, but only one of them is moving at a given time. The rest of them are all running, but they're on pause. They're just waiting to become the new top of the stack again. If we call another function, that function, the active frame goes on pause again. The function that was just called is put on top, and so on, until all of the function frames are finished. So let's take a look at a visualization of this and an example using the factorial function to see if we can help make this a little bit clearer. So this is the entirety of a factorial file, for example. And inside of that factorial file, I have 2 functions, fact, which is going to be a recursive implementation of factorial, and main, which basically just prints out the value of factorial, in this case, of 5. So we start at the beginning of main, and the first thing main does is it calls another function. It calls printf. As soon as it does that, main kind of is on pause. It's kind of hanging out right here, and it is waiting for printf to do its work. Well, what does printf have to do? It just has to print out a number, but it has to print out factorial of 5. But it doesn't know factorial of 5. It has to make a function call. So printf then goes on pause and waits for factorial of 5, which now becomes the new active frame. So in the factorial of 5 frame, what's happening? Well, we're passing in the value 5 to the fact function, and then it's going to check, well, is n equal to 1? No. So then it's going to return n times fact n minus 1. Okay, so now the factorial of 5 frame is basically calling a new function, passing in another call to factorial, passing in 4 as the parameter instead. So the factorial of 5 frame now goes on pause, and a frame for factorial of 4 becomes the new active frame. And it's going to go through the same process. Is 4 equal to 1? No. So instead it's going to return n times, in this case, or 4 times factorial of 3, another function call. So factorial of 4 frame goes on pause. Factorial of 3's frame becomes the new active frame. And we repeat this process again for factorial of 3, for factorial of 2, and then we get to factorial of 1. So at the very beginning, right when factorial of 1 is called, there are 7 function frames in the call stack. Factorial of 2, 3, 4, 5, printf, and main are all on pause at the lines that you see there. They're just kind of hanging out, waiting to become the new active frame again. But they're not moving from those arrowed indicators. So factorial of 1's frame begins. It asks the question, is n equal to 1? Well, in this case, the answer is yes. It's going to return 1. Now remember what happens when a function returns a value, that frame is done. It goes away. And that means that it gets popped back off of the call stack. And then the frame that is below it will become the new active frame. So factorial of 1 returns a 1. At this point, its frame is destroyed, and factorial of 2 can now get unpaused. Now factorial of 2 is that dark blue line on the left there, and it was waiting on the return value of factorial of 1. Well, factorial of 1 said, I returned a 1 to you, so factorial of 2 is going to return 2 times 1, or 2. It is now also returning, and so when it returns, it gets popped off the stack, its function frame is destroyed, and factorial of 3 becomes the new active frame. Factorial of 3 was waiting on factorial of 2, which returned a 2. So it's going to return 3 times 2, or 6. It returns a value. Its function frame is popped off of the stack. It is destroyed. Factorial of 4 becomes the new active frame. Factorial of 4 was waiting on factorial of 3. It got it back. It got its answer back of 6. So it's going to return 4 times 6, or 24. And it's going to return that value to factorial of 5, which has been waiting for factorial of 4 to finish its work. It returns 5 times 24, which is 120. When that frame is destroyed, now we resume at printf. Printf has that dark red line on the bottom there. It was waiting on factorial of 5, which just returned a 120. So what printf does is it prints out 120, and then its job is done. It doesn't have anything else to do. It's not waiting on another function call. And so it finishes executing. It doesn't return anything, but it reaches the last. It doesn't have anything else to do. So its function frame is destroyed. It gets popped off of the stack. And then all we have to do is see where main left off. Well, that was all main had. And so main's function frame will then pop off the stack as well, and this program will have completed its job by printing out 120. Hopefully that illustration of the call stack helped to show exactly how recursion works and how these functions are waiting and interacting with each other to allow the recursive process to occur. I'm Doug Lloyd. This is CS50. So far, it's likely that most of your programs have been a bit ephemeral. You run a program like Mario or Greedy. It does something, you maybe prompt the user for some information, prints some output to the screen, but then when your program's over, there's really no evidence that it was ever run in the first place. I mean, sure, you might have left it open in the terminal window, but if you clear your screen, there's really no evidence that it existed. We don't have a means of storing persistent information that exists after our program has stopped running, or we haven't up to this point. Fortunately, though, C does provide us with the ability to do this by implementing something called a file, a structure that basically represents a file like any that you would double-click on your computer if you're used to a graphical user environment. Generally, when we're working with C, we're actually going to be working with pointers to files, file stars. But except for a little bit when we talk about a couple of the functions that work with file pointers, you don't need to have really dug too deep into understanding pointers themselves. There's a little teeny bit where we will talk about them, but generally file pointers and pointers, while interrelated, are not exactly the same thing. Now, what do I mean when I say persistent data? What is persistent data? Why do we care about it? Say, for example, that you're running a program, or you've written a program that's a game, and you want to keep track of all of the user's moves so that maybe if something goes wrong, you can review the file after the game. That's what we mean when we talk about persistent data. In the course of running your program, a file is created, and when your program has stopped running, that file still exists on your system. And we can look at it and examine it. And so that program would be said to have created some persistent data, data that exists after the program has finished running. Now, all of these functions that work with creating files and working and manipulating them in various ways live in standard.io.h, which is a header file that you've likely been pound including at the top of pretty much all of your programs, because it contains one of the most useful functions for us, printf, that also lives in standard.io.h. So you don't need to pound include any additional files, probably, in order to work with file pointers. Now, every single file pointer function, or every single I/O function, file I/O, input-output function, accepts as one of its parameters or inputs a file pointer, except for one, fopen, which is what you use to get a file pointer in the first place. But after you've opened a file and you get file pointers, you can then pass them as arguments to the various functions we're going to talk about today, as well as many others, so that you can work with files. So there are 6 pretty common basic ones that we're going to talk about today. fopen and its companion function fclose, fgetc and its companion function fputc, and fread and its companion function fwrite. All right, so let's get right into it. fopen. What does it do? Well, it opens a file and it gives you a file pointer to it. So then you can then use that file pointer as an argument to any of the other file I/O functions. The most important thing to remember with fopen is that after you have opened the file or made a call like the one here, you need to check to make sure that the pointer that you got back is not equal to null. If you haven't watched the video on pointers, this might not make sense, but if you try and dereference a null pointer, recall, your program will probably suffer a segmentation fault. So we want to make sure that we got a legitimate pointer back. The vast majority of the time, we will have gotten a legitimate pointer back. It won't be a problem. So how do we make a call to fopen? It looks pretty much like this. File star ptr, ptr being a generic name for a file pointer, fopen, and then we pass in 2 things, a file name and an operation we want to undertake. So we might have a call that looks like this. File star ptr1 equals fopen file1.txt, and the operation I've chosen is R. So what do you think R is here? What are the kinds of things we might be able to do to files? So R is the operation that we choose when we want to read a file. So we would basically, when we make a call like this, be getting ourselves a file pointer such that we could then read information from file1.txt. Similarly, we could open file2.txt for writing, and so we can pass ptr2, the file pointer I've created here, as an argument to any function that writes information to a file. And similar to writing, there's also the option to append a. The difference between writing and appending being that when you write to a file, if you make a call to fopen for writing, and that file already exists, it's going to overwrite the entire file. It's going to start at the very beginning, deleting all of the information that's already there. Whereas if you open it for appending, it will go to the end of the file if there's already text in it or information in it, and it will then start writing from there. So you won't lose any of the information you've done before. Whether you want to write or append sort of depends on the situation, but you'll probably know what the write operation is when the time comes. So that's fopen. What about fclose? Well, pretty simply, fclose just accepts a file pointer, and as you might expect, it closes that file. And once we've closed a file, we can't perform any more file I/O functions, reading or writing, on that file. We'd have to reopen the file another time in order to continue working with it using the I/O function. So fclose means we're done working with this file, and all we need to pass in is the name of a file pointer. So a couple slides ago, we fopened file1.txt for reading, and we assigned that file pointer to ptr1. Now we've decided we're done reading from that file. We don't need to do any more with it. We can just fclose ptr1, and similarly could we fclose the other ones. All right, so that's opening and closing. Those are the two basic starting operations. Now we want to actually do some interesting stuff. And the first function that we'll see that will do that is fgetC. File, get a character. That's what fgetC generally would translate to. Its goal in life is to read the next character, or if this is your very first call to fgetC for a particular file, the first character, but then after that you would get the next one, the very next character of that file, and stores it in a character variable, as we've done here. Char ch equals fgetC, pass in the name of a file pointer. Again, it's very important here to remember that in order to have this operation succeed, the file pointer itself must have been opened for reading. We can't read a character from a file pointer that we opened for writing. So that's one of the limitations of fopen, right? We have to restrict ourselves to only performing one operation with one file pointer. If we wanted to read and write from the same file, we would have to open two separate file pointers to the same file, one for reading, one for writing. So again, the only reason I bring that up now is because if we're going to make a call to fgetC, that file pointer must have been opened for reading. And then pretty simply, all we need to do is pass in the name of the file pointer. So char ch equals fgetC ptr1. That's going to get us the next character, or again, if this is the first time we've made this call, the first character of whatever file is pointed to by ptr1. Recall that that was file1.txt. It'll get the first character of that and we'll store it in the variable ch. Pretty straightforward. So we've only looked at 3 functions and already we can do something pretty neat. So if we take this ability of getting a character and we loop it, so we continue to get characters from a file over and over and over, now we can read every single character of a file. And if we print every character immediately after we read it, we have now read from a file and printed its contents to the screen. We've effectively concatenated that file on the screen, and that's what the Linux command cat does. If you type cat and then a file name, it will print out the entire contents of the file in your terminal window. And so this little loop here, it's only 3 lines of code, but it effectively duplicates the Linux command cat. So this syntax might look a little weird, but here's what's happening here. While ch equals fgetC ptr is not equal to eof. That's a whole mouthful, but let's break it down just so it's clear on the syntax. Because I've consolidated it for the sake of space, although it's a little syntactically tricky. So this part in green right now, what is it doing? Well, that's just our fgetC call, right? We've seen that before. It's obtaining one character from the file. Then we compare that character against EOF. EOF is a special value that's defined in standardIO.h, which is the end of file character. So basically what's going to happen is this loop will read a character, compare it to EOF, the end of file character. If they don't match, so we haven't reached the end of the file, we'll print that character out. Then we'll go back to the beginning of the loop again. We'll get a character, check against EOF, print it out, and so on and so on and so on, looping through in that way until we've reached the end of the file. And then by that point, we will have printed out the entire contents of the file. So again, we've only seen fopen, fclose, and fgetC, and already we can duplicate a Linux terminal command. All right, so as I said at the beginning, we had fgetC and fputC, and fputC was the companion function of fgetC, and so as you might imagine, it is the writing equivalent. It allows us to write a single character to a file. Again, the caveat being, just like it was with fgetC, the file that we're writing to must have been opened for writing or for appending. If we try and use fputC on a file that we've opened for reading, we're going to suffer a bit of a mistake. But the call is pretty simple. fputC capital A ptr2, all that's going to do is it's going to write the letter A into file2.txt, which was the name of the file that we opened and assigned the pointer to ptr2. So we're going to write a capital A to file2.txt, or we'll write an exclamation point to file3.txt, which was pointed to by ptr3. So again, pretty straightforward here. But now we can do another thing. We had this example we were just going over about being able to replicate the cat Linux command, the one that prints out to the screen. Well, now that we have the ability to read characters from files and write characters to files, why don't we just substitute that call to printf with a call to fputC, and now we've duplicated cp, a very basic Linux command that we talked about way long ago in the Linux commands video. we've effectively duplicated that right here. We're reading a character, and then we're writing that character to another file. Reading from one file, writing to another, over and over and over, again, until we hit EOF. We've got to the end of the file we're trying to copy from, and by that point, we'll have written all of the characters we need to the file that we're writing to. So this is CP, the Linux copy command. Okay, so at the very beginning of this video, I had the caveat that we would talk a little bit about pointers. Here is specifically where we're going to talk about pointers in addition to file pointers. So this function looks kind of scary, right? It's got several parameters. There's a lot going on here. There's a lot of different colors and text. But really, it's just the generic version of fgetc that allows us to get any amount of information. It can be a bit inefficient, right, if we're getting characters one at a time, iterating through the file one character at a time. Wouldn't it be nicer to get 100 at a time or 500 at a time? Well, fread and its companion function fwrite, which we'll talk about in a second, allow us to do just that. We can read an arbitrary amount of information from a file, and we store it somewhere temporarily. Instead of being able to just fit it in a single variable, we might need to store it in an array. And so we pass in 4 arguments to fread. A pointer to the location where we're going to store information, how large each unit of information will be, how many units of information we want to acquire, and from which file we want to get them. Probably best illustrated with an example here. So let's say that we declare an array of 10 integers. We've just declared it on the stack arbitrarily, int r10. So that's pretty straightforward. Now what we're doing, though, is the fread call is we're reading size of int times 10 bytes of information. Size of int being 4. That's the size of an integer in C. So what we're doing is we're reading 40 bytes worth of information from the file pointed to by PTR, and we're storing those 40 bytes somewhere where we have set aside 40 bytes worth of memory. Fortunately, we've already done that by declaring ARR, that array right there. That is capable of holding 10 4-byte units. So in total, it can hold 40 bytes worth of information. And we are now reading 40 bytes of information from the file, and we're storing it in ARR. Recall from the video on pointers that the name of an array, such as ARR, is really just a pointer to its first element. So when we pass in ARR there, we are in fact passing in a pointer. Similarly, we can do this. We don't necessarily need to collect our, we don't need to save our buffer on the stack. We could also dynamically allocate a buffer like this using malloc. Remember, when we dynamically allocate memory, we're saving it on the heap, not the stack. But it's still a buffer. It still is, in this case, is holding 640 bytes of information because a double takes up 8 bytes, and we're asking for 80 of them. We want to have space to hold 80 doubles. So 80 times 8 is 640 bytes of information. And that call to fread is collecting 640 bytes of information from the file pointed to by PTR and storing it now in ARR2. Now we can also treat fread just like a call to fgetc. In this case, we're just trying to get one character from the file. And we don't need an array to hold a character. We can just store it in a character variable. The catch, though, is that when we just have a variable, we need to pass in the address of that variable, because recall that the first argument to fread is a pointer to the location in memory where we want to store the information. Again, the name of an array is a pointer, so we don't need to do ampersand array, but C, the character C here, is not an array. It's just a variable. And so we need to pass in ampersand C to indicate that that's the address where we want to store this 1 byte of information, this one character that we're collecting from PTR. Fwrite, I'll go through this a little more quickly, is pretty much the exact equivalent of fread, except it's for writing instead of reading. Just like the other, we've had open and close, get a character, write a character. Now it's get arbitrary amount of information, write arbitrary amount of information. So just like before, we can have an array of 10 integers where we already have information stored, perhaps. So there's probably some lines of code that should go between these two, where I fill ARR with something meaningful. I fill it with 10 different integers. And instead, what I'm doing is writing from ARR. I'm collecting the information from ARR and I'm taking that information and putting it into the file. So instead of it being from the file to the buffer, we're now going from the buffer to the file. So it's just the reverse. So again, just like before, we can also have a heap chunk of memory that we've dynamically allocated and read from that and write that to the file. And we can also have a single variable capable of holding 1 byte of information, such as a character. But again, we need to pass in the address of that variable when we want to read from it. So we can write the information we find at that address to the file pointer PTR. There's lots of other great file I/O functions that do various things besides the ones we've talked about today. A couple of the ones you might find useful are fgetS and fputS, which are the equivalent of fgetC and fputC, but for reading a single string from a file. Instead of a single character, it'll read an entire string. fprintf, which basically allows you to use printf to write to files. So just like you can do the variable substitution using the placeholders %i and %d and so on. With printf, you can similarly take the printf string and print something like that to a file. fseek, if you have a DVD player, is the analogy I usually use here, is sort of like using your rewind and fast forward buttons to move around the movie. Similarly, you can move around the file. Is one of the things inside that file structure that C creates for you is an indicator of where you are in the file. You're at the very beginning at byte 0. Are you at byte 100, byte 1000, and so on? You can use fseek to arbitrarily move that indicator forward or backward. And ftell, again, similar to a DVD player, is like a little clock that tells you how many minutes and seconds you are into a particular movie. Similarly, ftell tells you how many bytes you are into the file. feof is a different version of detecting whether you've reached the end of the file. And ferror is a function that you can use to detect whether something has gone wrong working with a file. Again, this is just scratching the surface. There's still plenty more of file I/O functions in standardio.h, but this will probably get you started working with file pointers. I'm Doug Lloyd. This is CS50.
მოკლედ ეს არის დღევანდელი შეხვედრა მთლიანად და შევხვდებით სამშაბათს. რაც შეეხება ამ წუთას დავალებებს, დავალებებიდან დევს ლაბი მეოთხე ლაბის დავალება დევს უკვე. დანარჩენი ეს ბმულები სამშაბათს გააქტიურდება. ხო, კიდე და აქ დაგემატებთ ახლა სამშაბათამდე დაგემატებთ ყველა თემაზე გამოყენებულ კოდებს, source კოდებს და პრეზენტაციებს, რასაც ეს ადამიანები ლექციებზე რასაც გიჩვენებენ ხოლმე რა. ეგ იქნება. თუ კითხვები გაქვთ, შეგიძლიათ Facebook-ზე მომწეროთ. დანარჩენი შევხვდებით, როგორც გითხარით სამშაბათს. წარმატებები ბედნიერად.